So hello everyone. I think today, as requested, we'll be going through the hands-on for decision tree as well as random forest. Well, it makes sense to do random forest along with decision tree because it is generally a continuation. Because in real world, in practice, when you make one type of model, you don't stop there. You keep on, you keep on trying to improve it by iterating over it, probably changing features, probably doing something on the cleaning side or processing of the data side, probably on the feature side, or in this case, what we are going to look today is, changing the model itself. And what I'm trying to do today is I'm trying to give you an end-to-end flavor of how things work in the industry. It is very, very beginner friendly. There are many other things that are there, but let's start with this. If it goes good, we can, go into much more details. Okay. All right. Getting into the details. So the data that we have is we are going to talk about Titanic data. Okay. So this is a really popular data that is available online and is freely available. Okay. So here, these are the features that or the columns that the data has. Okay. These are the columns like passenger ID, survived, whether the person survived or not survived. What was the name of the passenger class. Okay. There were different classes in which they were traveling. Then what was the cabin number, age, number of siblings they had, number of parents or children they had, okay, ticket number, fare, cabin number, and all that. Embarked, where from which port did they start their journey? Okay, there were three um stations or ports where the passengers could on board their journey, and they are these these three. So yeah, uh, having said that, let me add a few cells here. Let me add a few cells here. Well, this is the data, what we are going to look into. Let me show you from where the data comes in. So it's very important that you guys practice. Uh, and that's why some of the data sets are already inbuilt, okay, with some of the libraries. sklearn has a few um, data sets within it. Okay. And what we are going to load is going to come from a Seaborn library. Even the Seaborn library, they have an inbuilt data sets that you guys can, load in for your practice. Okay, cool. So that's the whole purpose. I want to show you how you can do this and encourage you guys to go back and, do this at your end as well. Cool. The first step is import the libraries. There are a few libraries that we need. Import pandas, numpy. We also need from sklearn dot pre-processing pre-processing. We need to import the label encoder. We also need standard scalar. Test train split. Yes, that is good. This we don't need. And here, along with this, we need classification report. We also need the ROC curve and the AUC. Okay, so this will suffice. This will suffice for now, and then we will also go and for the model, since we want to use decision trees and random forest. So let me go ahead and uh, import them as well from sklearn.tree. In tree you have the decision tree classifier, and you have in ensemble in sklearn, from sklearn.ensemble we can import our random forest. Okay. Yeah. I think then the other thing I want to show is since we spoke about hyperparameter tuning, in that we looked at your grid search as well as random search. So I want to, with the time, I want to show that. Let's see if time permits, we will look into it. Okay, let's run this. Let's run this. And here, what we can do is then let's load the data set. And in data set, what we have is Titanic. Let's call it Titanic. Simple for us to remember. How you can load the data set is very good. Just simply say load dataset, sns.load dataset, and the data that you want to load. So there are many other datasets that are available. Okay. And let us quickly do and see how many, what is the shape of the data. So the data has 891 rows and 15 columns. Let me show you. Let me show you a couple of first five entries with head. Now head by default will give you five rows. But if you want to look at a smaller number, you can just pass in two there. If you want to see 10, do this. And you can also also look at the tail as well. Not only from the start, you can also look at the tail. By default it will have five. Okay. All right, all right. So let's see, guys. Let's look at the data. Whenever you start any kind of analysis, okay, in any domain, anytime, okay, no matter whether you're doing classification, regression, or whatnot, just spend some time with the data, okay? That will help you. That will help you. Now, let us spend some time with the data. So survived here is our target variable. We want to predict whether the person who onboarded Titanic uh, was he or she able to survive or not. Okay. Zero means no, he or she was not able to survive, and one means yes, they were able to survive. Okay. Passenger class, there are different classes. The sex of the passenger, male or female, age, then siblings, parent or child number, what was the fare that they gave. So if you can see, there is a huge difference between fares. Okay, depending on where they started from. If the journey was smaller, then obviously the fare would be there, and also the class of like in planes and in trains we have classes, right? Even Titanic ship or even the cruises, they have their classes. Who, whether the person is man or woman, adult, male, true or false, deck, so on which deck they were staying, embarked town, exactly, embarked, it's exactly the same. It's just that here we have initials and here we have the entire name. Alive, whether they are alive or not, and were they alone or not. Okay. Now, if you look at this really clearly or closely, I think there are a few columns which are repeating, right? Embarked and embarked down. They're essentially giving us the same information. Okay. There's no new information coming from there. Okay. Even here, your sex, which is giving us male and female, who is also telling us whether it's man, whether the person is man or women. Adult male is also kind of giving us the same, information. So there is no new information coming from these. They are just redundant columns. Even if you say alive, alive is exactly your target variable. So this is really, really critical that when you're training, when you're, going and training a model, do not pass your survived as well as alive. It's just going to say that, okay, if alive is no, survived is zero. So it's that's not right way. Alone, I think whether the person is alone or not can be calculated if they do not have any siblings, okay, on board, and if they do not have parents or children also onboarded, then of course they are going to be, alone. If you look at this true is coming where both of these are zero, and wherever it is false, you will see either a number in this column or this column. Okay. So having said that, now that is a good thing that we have seen. We have understood the data, what it means. And typically whenever I start my understanding of the data, I also try to look at this. I also try to look at the information. It is a very clear way to see that, okay, what all columns you have. Okay, it will also give you the what do you say, the number of rows and columns. Okay, it will say that it has 15 columns, it has 891 rows, and then for each column it will tell you whether it has a null value or not. Okay, like for this age has a few null values, right? deck deck out of 891, 203 are the only rows where we have values. So it doesn't make sense to include this variable, because more than half, in fact, I don't know, a one-fifth, close to one-fifth, one-fourth is empty. So there's no way, even if we impute it, it's going to help us. Okay. Age, we can try imputing. We can do missing value treatment for the age, but because it has 700 out of 891, we have the values for. And what else? Yeah, embark town and embark also has 889 non-null values, meaning there are two missing values. And here it clearly says what is the D type of each of this variable. Each of these variable, what is the D type? Okay, cool. And sometimes when you're dealing with huge data, no, this or small data, this helps. It will tell you how much memory it is using. Okay. Then typically I also do describe on the data. I also do describe on the data. It will, it helps me to see for all the numerical data, what is the count, okay, that we already saw in the info part, but it also gives the standard deviation, the minimum value, the 25 percentile, the median. 50 percentile is nothing but median. Then you have 75 percentile and the maximum value. Okay, and the maximum value. So if you look at this clearly, or closely, are you seeing the maximum value is 512 for the fair, whereas median is only 14. 75 percentile is also 31, meaning 75% of the people paid 31 or less, but still the maximum price is 512. It says that there are some outliers. There are some outliers. What else? What else? We do not see much here. Okay. Even in age, even in age, even in age, 75% of the people are below the age of 38, whereas maximum age is 80. Okay. So what about this? PRs, yes, this is also looking like, majority of them are coming alone. They do not have any parent or children, but 75% of the people, they do have your, what do you say, sibling. Not 75% of the people, but 75 percentile. Okay, cool, cool. Now let me let us get started. Okay, let us get started as to what what all can we look into the data. Okay, cool. Now let's first try to handle, let's first try to remove the unnecessary columns. And which are these? Which are these? It is telling us deck. Um, Deck also is kind of unnecessary because even imputing that value is not going to help us. Okay. Embark town was one, alive was one, alone was one. What else? Who was there, right? Who and adult male. Who and adult male. Who and adult male. And what else? Nothing else, right? So who, adult male. Yeah, yeah, looks like it. Looks like this. Okay, let's do that. And now let's handle the missing values. Let's handle the missing values. Before we handle missing values, we also know if there are any missing values. Okay. Let me put it here along with this. So here what we can do is of the dataset Titanic, we can do how many of them are null. Okay. How many of them are null? Now, if you see your survived has 0 null values. What is it doing? It is taking all the null values of each column and then summing it. You see, age has 177 missing values. Age has 177 missing values. And embarked has only 2 missing values. And embarked has only 2 missing values. Okay. So let's try to handle them. Let's try to handle them. Let me copy this and call this finding missing values in the dataset. And here we will say this. So essentially, what can we do? What are we going to do? Since 2 is pretty small number, okay, 2 is pretty small number. I'm showing you two ways. When the number of missing values are really huge, drop that entire column. That's what we did with deck. If the number of missing values are very small, like teeny weeny, 2, 3, like embarked, drop those 2 rows. Okay, don't drop the column, just drop 2 rows. But you have somewhere like age where missing values are, not really high, not really low, but something that can be imputed, then we will impute it. Okay, then we will impute it. Let's try to impute. Let's impute the Titanic. Okay, Titanic, embark. No, we don't want to do that. We want to drop this. Titanic. So, NA, where I want to drop NA based off my embarked column. Okay, based off my embarked column. All right, and we are going to take this in place is fine. See, let's run this. We need to do in place equals to 2, and if we do that, this is what I want. Let's try to see. There you go. Okay. Now let us confirm that we don't have any missing values now. Let's confirm that by doing a shape of Titanic. The shape should now have, we removed 6 columns. So from 15, we came down to 9 columns. And we have removed, out of 891, we have removed two rows. Now that's why we are now left with 889. Okay. So that confirms, that confirms. Now, what is the next step? What is the next step? Next step is, let's visualize, or, let's visualize the target variable. Well, you can do value counts also on the target variable, but you, if you visualize it, it looks good. It looks good. So let's try to visualize this with matplotlib. We are going to say big size. I am going to create a small one. Okay, I'm going to create a small one. 5,5, and then we are going to create a count plot on survived. Data is Titanic. Okay, let's see. Let's see. Okay. So now it doesn't have the labels. We can put in the labels. Let's put in the labels, but it is looking like the data is not imbalanced. This much of difference works. It is slightly imbalanced. Now you can go ahead and make the data set imbalanced. Okay. But generally this is not called imbalanced. Okay. But it is your personal preference. If you want to train your model on a 50-50, you can do that, but there's hardly going to be any difference. Okay, there's hardly going to be any difference. Okay, you can also do this thing. You can also do this thing. I can nick while dot value counts. Okay, so it will give you the count also here. Instead of visually, if you want to look at this, you can do this. Okay, cool. Now, once you have confirmed that it is not a imbalanced data set, you can go ahead and start going into details. Now let's try to see if there are any outliers. Okay, if there are any outliers, because when we were looking at the data in describe, we noticed that the fare was having really high numbers, and I also suspect age is also the same. Okay, age is also the same. So let's try to visualize these columns. Visualize the visualize for outliers using boxplot. Now, I hope you guys remember what boxplot is. So here plt dot figure. Again, let's create a small one. And I want to create subplots. I don't want to, create multiple. So I'll create side by side subplots, which is done by plt dot subplot. Okay, let's see. Yes, this is what this says is one row and two columns. This, and then you're talking about the first one. This says one row and two columns is what you want to have. And here you're going to plot the second one. Here you're going to plot the second one. Let's also give them the title, and the title would be age versus survived. Um, it's not actually age versus survived. It is age distribution itself. And here we have title fair distribution. Let's get rid of this, and we can now run this. There you go. There you go. So if you remember box plot, this is what? This is your 25 percentile. This is the median, and this is your 75 percentile. In age, after this whisker, there are so many points. above 52, 53 something, it is way higher. And all these dots are nothing but your outliers. This is also your outlier. So basically, how do you identify your sorry, how do you identify your IQR or interquartile range, or your outlier is using an interquartile range, which is IQR. Okay. IQR is nothing but, IQR is nothing but your 75 percentile, your 75 percentile plus 1.5 times the interquartile range, meaning 75 to 25, whatever the difference is, multiply, add that to the 75, you will get the upper bound, and you will multiply it by either 1.5 or 2, depending on what your domain is and what you feel like. Okay. Generally, thumb rule is 1.5, but I personally have also used 2 when I don't want to create a very strict outlier treatment. Then I have stick with 2 and sometimes even 2.5. But typically, thumb rule is 1.5. Okay. So this blue is your interquartile range. 1.5 times of this 75, add on top of it, you will get this 1.5 times this interquartile range from below the 25 percentile will give you this, and anything above and below this are your outliers, are your outliers. Okay, are your outliers. Cool, cool, right, right. Mm, just trying to gauge why is it what the box plot. Why I changed that is because I was seeing that with the autofill, the survived was coming and I was getting two box plots here. That shouldn't be the case, even though it was showing the right value, but age also had a different one there basis the survived. So it was giving us two box plot. If survived is 0, how did the age look like? If the survived was 1, how did the age look like? Okay, that's what it was giving. But I just want to look at age individually, irrespective of my target variable. That's also you can do, by the way. Fair also, if you see, as we suspected, as we suspected, it also has many outliers. It also has many outliers. All right, let's try to solve it. Let's also first calculate the outlier um, statistics. Here we will try to find whatever I said in words. Let's try to find if we can print it. What is your lower bound? What is your upper bound? What is your IQR and all that? Okay. So Q1 will come from my quantile. My 25 quantile is Q1. Q3 is my 75 quantile. IQR is nothing but Q3 minus Q1. This blue region. This is my Q3, this is my Q1. So what is the difference between these two is my IQR. Now, to find the lower bound, as I told, lower bound is nothing but Q1 minus this Q1 minus 1.5 times of IQR, and upper bound is nothing but 75 percentile plus 1.5 times of IQR. Now, those are your lower bound and upper bounds. Anything above this and anything below this are outliers, okay. So you can, this number can be either 2, 2.5 depending on your use case. Thumb rule is 1.5. Thumb rule is 1.5. Okay, cool, cool. Let's, you know, we need to calculate this for both the columns, right? For age as well as this. So we are going to calculate the lower bound and upper bound for both of them. And then what we are going to do is we are going to we are going to store the outliers, identify the outliers, and then we are going to treat the outlier. What are you going to treat it with? You are saying anything above upper bound is an outlier. So cut that value till the upper bound. The maximum value that my age can be is my upper bound. Okay. So that is the idea. Even the lower bound. Even the lower bound. Okay. Even the lower bound. So this is this. Print number of outliers in this. That is fine. We can also print other few things here. Print the outliers. This is that percentage will also come in here. Okay. And we can also print for your benefit. We can also print the Q1 and Q2. Q1 is nothing but this, IQR this, and we can also print the lower bound. Lower bound is nothing but my, and we can also print the upper bound. Copy. Okay, let's do that. And then finally, what we want to do, we also want to impute it. We want to clip it. We want to clip it to the upper bound. All the values above the upper bound, we want to clip it at upper bound, and all the values below the lower bound, we want to clip it at the lower bound. Okay, let's do that. Let's do that. So here we are going to say Titanic, if my age is greater than equal to lower bound, okay, and if my age is less than equal to upper bound, this is removing the outliers. We don't want to remove the outliers. We want to clip the outliers from the data set. So here what we can use is, why I'm showing you this is, there is this function called clip, and you can simply use it to clip your outliers. And here, since we are inside this for loop, what we can do is we can use the column instead of age. We can do this, and after we do this, let us print here number of outliers after clipping. Okay, number of outliers after clipping. It had to be generalized. Now outliers are all those which are, since everything is inside the for loop, this had to be column. Okay, It's good that you guys are seeing all this. So let me do one thing. Let me read the data set again. Let me read the data set again. Let me drop it here. This should still be the same. Yes. Then let's impute it. This is should be same. This should be same. Let's see if we are getting the same graph again. Yes, we are. And let's, I just want to make sure there's no age here again. Yes. Okay, so now this will give you a better picture where in age there were 65 outliers, 7.31%. This were the statistics, and after clipping we are left with 0 outliers. Okay. Similarly, for fair we had 114. We had 114 outliers, which is nothing but 12.8%. And these are the statistics basically. And after clipping, we are again left with 0. Okay. Now here, if you see, the lower bound is coming out to be minus 26. We did not take care of it, but typically when you think, that's why I keep saying that you need to keep in mind what you are doing. So when fair cannot be negative, right? Fair cannot be negative. So what you will do is you will try to say that if you are going to take maximum of your lower bound and 0, maximum of 0, okay, or lower bound, whichever is maximum. So you will say that if anything is below 0, that is an outlier. Okay, cool, cool. The next part is data processing. Now in data processing, what we do is in data processing, we will process the data in such a manner that it is ready for your machine learning. It is ready to build your ML model. Okay. Which model? So data processing will change depending on the ML model that you're going to implement. Probably in some, the format of the data is required in one specific manner. In the other, it's in a specific manner. Okay. So we'll cover this in detail. If we continue to do this through videos, I think I'll be happy to walk you through other techniques that are required in data processing. Okay. Okay. So now, without a further ado, let's get into this. So since we've done so many things, let's good to go back and print out the info here, and let's make sure we have everything that we need. So survived is our target variable. P class is nothing but your passenger class. Sex of the person, the passenger, age, whether they have siblings or no, the count of siblings onboarded, parent or children, fare, embarked, and class. Class, we have class also, and it is a category type. Class and P class are similar, are same. Did we miss it? Did we miss it dropping? Let's see. So class here is third, first, third. It's no it's the same redundant column. It's the same redundant column. So you see here, this class is just giving you things in words, but here it's numeric. Okay, so for us, we don't want words. It works good, the model works good on numeric data, so we're going to get rid of this class. We should have gotten rid of this earlier. We should have gotten rid of this earlier when we were dropping the columns. We should have done this here itself, but doesn't matter, we'll do it once again. Okay, it's good we caught it, otherwise it's you know it could interfere with fitting of the model. So with the experience, so you also try to do this. Once your data cleaning is complete, try to check things. Double sure. Do always QC. QC is quality check. Make sure you've done all the things correctly. Okay. Cool. So let's get rid of this. So which was that column? It is this class that you want to get rid of because it is the same column as P class. Let's do that. Let me write a quick comment on this. Remove the array column class. Okay, let's remove it. Let's add a few cells in here because we might be needing them. Then in data processing, the first step is encoding. You encode your label. You encode your label. Okay. You see where encoding is required, where encoding is required, where encoding is required here. Encoding is required here in your sex column and in your embarked column. So let's do encoding. So we are going to encode the categorical variables. Now, you might be asking why was this not done in data cleaning? Because some of the algorithms, right? Some of the algorithms, they can handle categorical features as it is. Okay, like some of the advanced algorithms like light GBM. Over there, you just need to pass the list and just say category is equal to the name of those columns, and it will automatically, take care of it. So some advanced algorithms, they have different things. So that's why I said, you know, uh, you need to make sure data processing is separate from cleaning. Cleaning is all the repetitive stuff. Processing is specific to the set of algorithms that you want to implement. Okay, cool, perfect. So this is how we have encoded. We are going to use label encoder, store it in LE, and then here, this is coming in pre-processing. If you look at this label encoder, I imported it from pre-processing. Okay, okay. Then the other thing is we will also scale it. We will also scale it. Let's come back here. We will also scale it. So we are going to before scaling, sorry, before scaling, we need to set our columns, right? Which are the features, which are the target variable. Let's fix that. Let's fix that first. So prepare features and target. Okay. And our x is nothing but our x is nothing but everything except the survived. Our target variable is survived, right? We need to predict whether the passenger survived or not survived. Okay, 0 or 1. Binary classification here is what our problem is. So we have defined our y and x. Then let's run this. We have run label encoding. I don't think so. Let's run it again. Here also we will run it. And then the next step is to scale the features. Why do we do scaling? Is because to make sure that all the features, independent features that you have, they're on the same range. If one of the feature is really high or has a different what do you say range, it can overpower some of the other features. If it is very small, the range is very small, then it might be not considered at all, even though it is meaningful. Okay, so that is the reason why we do scaling. But we can also it is not a mandatory step, but a good practice kind of a step. In some cases where the ranges are similar, you might not you can ignore this step also. Why I'm saying that is that if you have let's say you're trying to predict the age of a person using the weight of the person and the salary of the person. So salary can be in thousands, lakhs, right? And the weight can be in a different unit, but the range is going to be somewhere between 30 to maximum 100 or 120. I don't know. Okay. Whereas your salary can be starting from 10,000 to lakhs. So the range is pretty huge, and along with other features. So that's the reason why we do scaling. So once you do that, let's call let's call this as y. We will call this as x scale, so that we are able to distinguish between our x and normal scaled x. Cool. Then here, what I'm going to do is I'm going to store this as a data frame. I'm going to store this as a data frame where x scaled is going to be my values, and columns I'm defining with whatever the columns that I had in x. Okay. Okay. Cool. Let's run this. Let's run this. Now, the next step. What is the next step? I think you've already seen, or you might be familiar, that we need to split the data into train and test. We need to split the data into train and test. So split the data. So it is going to come from, yeah. So we are going to say 80-20 is our split, and we are going to use x scaled here. We are going to use x scaled here because x scaled is our scaled independent features. Okay, they are our scaled independent features, and let's also print it here. Let's print train. Let me say x train is equals to this, x is this. Let me say print, well, not x test. I want y train, and here I will say y train. Okay, and let me put a distinction between these two so that it is clear. Well, it's not required. It's not, something that is, yeah. So you have that. Let's get rid of this train part. I think we already have. Cool. So let's run this. And now what you see, we had how many rows? We had 889, right? So 889 into 80% is how much? 889 into 0.8 is 711.2. So that is what you're getting. 80% is in your train and 20% is in your test. Okay, clear? Cool. Now we have split our data. Now is when the magic is going to start. All of you were waiting for this, right? Decision tree. I'm going to say without tuning. Okay, without tuning. So decision tree, what do we do if we have to fit? We will train the decision tree. We will train the decision tree. First, you are going to say it is, let's say, DT model. We're going to use DT model, and then you're going to fit it. What's the next step? After you have fitted, what is the next step? The next step is to predict. Let's do that. Predict using the DT model. So it is going to do ypred, let's call it ypred underscore DT. And we will also evaluate the model with accuracy. Here. One more thing that I want to show you This we will compare in the end, but I also want to show you time taken by these models to fit, by these models to fit. Okay, so we are going to define start as start time, and we are going to end, and we are going to say dt time is equals to your time now. And yes, we've got this one print statement. Let's call it here. Let's get all our printing statements here separately. It's a personal choice. You can have it there also. It doesn't matter. Printing the. So let's say how much time it took here. And I'm also going to say this is the accuracy. You know what? I will comment it out. That's how you will get the accuracy, but I want to cover the overfitting also with this. So I want to give you an idea of overfitting also. So what I'm going to do is I'm going to calculate my train accuracy, and my train accuracy is nothing but accuracy accuracy score accuracy it is going to be it is going to be accuracy. This needs to be in curly braces. Accuracy underscore score, and we are going to say y train and yf. y train and the predictions if we were to predict on the train. So we already have the actuals and we are predicting it on the train rather than on the predictions. In reality, you'll be doing the predictions on test only. In reality, you'll be doing predictions on test only. But here, if you want to know what is your train accuracy, you have fitted the model here. You need to predict it also on the train. Okay. This is a little advanced stuff, but uh, I hope this will be clear. Okay. So what do we have? We have time taken, we have accuracy, test accuracy. What else? That's it. That's it we want to do. And let me also print here decision tree without tuning. Okay. So that all the details are here. And since we are doing classification, let's print out the classification report as well. Let's print out the classification report as well. Okay. Cool. And this, okay. Now, what are we seeing? What are we seeing here? What are we seeing here? We are seeing that the time taken to fit is 0.02, and this is nothing but rounding off, guys. This is nothing but rounding off. 0.02 seconds. Train accuracy is 0.98, meaning 98%. What is your test accuracy? 75. Here is your recall. Oh, sorry. Here is your precision. Here is your recall F1 score. Okay. Okay. Cool. Cool. Now, this is for decision tree. If I want to do the same thing for random forest without tuning. If I want to do the same thing here for random forest, what I can do is I can simply copy paste rather than calling decision tree here. We will call random forest classifier. We will say this is RF model. Rest everything is same. You see how consistent it is, how beautiful it is. Changing the algorithm is just like this. Changing the algorithm is just like this. I'll be changing more in the printouts. Random forest without tuning. Okay. So here what we want is we don't want DT time. This is called RF time. Time taken to fit a random forest model. And we are going to do that. And this again, prediction on the train is going to come from RF model. And this should become RF. Let's change that here also, RF. Okay, cool. And this will also become RF. Am I missing anywhere, anything? Let's see. Cool. So how much time did this take? How much time did this take? It took more time, right? It took more time than decision tree. Decision tree is only one tree. Random forest is, here we have not given it any parameters. We have not given it any parameters. So by default, how many trees it's going to make? 100. By default, it is going to make 100 trees. Let's look at it. N estimators 100. By default, it will create 100 decision trees. So it is taking more time. Okay, cool, cool. This is your precision. This is your recall. 0, 1 here is nothing but for survived 0, for survived 1, what is the precision and so on. Okay, and F1 score. So you see already F1 score is better. F1 score is better. Precision is also better. Recall. What about recall? Recall is also better in random forest. Okay, cool. So obviously, what we are now getting is looking at the train and test accuracy. Random forest is also overfitting here. Why? Train accuracy is 98%. Test accuracy is how much? Only 77%. Whereas in your decision tree, the train accuracy was 98% and test accuracy is 75. So definitely that randomness that is happening in random forest is helping it reduce variance, overfitting. But still it is overfitting. Still it is overfitting. You see how much of a difference? 20% of a gap is there. 20% of a gap, 21% of a gap is there between train accuracy and your test accuracy. Okay, cool, cool. So what do we do now? What do we do now? Now that is where I want to show you guys hyperparameter tuning. Now, hyperparameter tuning is what we are going to look at. Okay. In hyperparameter tuning, now we already know my random forest is performing better than decision tree. In real world also, you will say that random forest is performing better. Why should I even tune my decision tree unnecessarily? You can go ahead and do that if you want to, make sure everything is to the T. But you can also say that my random forest is working good. Let me do hyperparameter tuning only for random forest. If you want, you can practice decision tree also with hyperparameter tuning. But here I'm going to show you only random forest. The things are going to be exactly the same. Okay. Part of few parameters, everything is going to be the same. So let's do one thing. Let's first look at grid search. Let's first look at grid search method. Grid search CV. This is what you're doing is you're doing cross validation. You're doing cross validation, meaning you're dividing your train part also into multiple small chunks. and saying rather than learning everything in one go, learn this much and remove out this much. Learn this much, remove out this much. Learn this much, remove out this much. I'll show you. It will be very, very clear. Cross validation. Cross validation. If there is an image, yeah, there you go. So this is five-fold cross validation. Five-fold means you are going to cross validate 5 times. What you're doing here is, in reality, you are dividing your data into train and test. You're dividing your data into train and test already. Now, when you do cross validation, you will say, I am going to divide my training data into 5 folds, 5 equal chunks. Again, you're dividing your train into 5 equal chunks. In the first iteration, split one, you're going to remove the fold one and you're going to fit your model on these 4 of them. And you're going to validate how is my performance looking like on first fold. Then in the second iteration, you will leave second fold and train on these green ones. Similarly, third, remove the fold 3 and learn on fold 1, fold 2, fold 4 and 5 and so on. Keep on removing one fold from each of these iterations. What it does is it will show your model different patterns. You are removing some part of the data and asking it to train it on this one. Then you're removing some other part from the data, putting this back and asking, okay, learn the pattern here. So that's the technique of cross validation. That is the technique of cross validation. And grid search, we have already seen. Grid search is nothing but it is going to create a grid of the parameters, the combination of the parameters that you want to choose, and it is going to give us the best parameter. Let's look into this. Let's look into hyperparameter tuning. So I think we have already imported GridSearchCV, right? Or no? Oh, no. Okay, let's do it here then. Let's come back. Let's come back and we are going to say from model selection, we are going to pull GridSearchCV. We will also pull RandomizedSearchCV. Let me not pull it now because I want to show the comparison between both of them since we have covered both of these in our sessions. So let's not go there as of now. But in GridSearchCV, what you need to do is you need to first define your parameter grid. Parameter grid. Let's say I want max depth to be none 10. Let's also experiment with 5. Okay. Let's also experiment with 5. And then which is the other parameter that you want to test? Which is the other parameter? What can we take? We can take any one of them. You can include all of them also. You can include all of them also, but I am just restricting myself with this minimum sample split. Minimum. Let's copy it. Let me put it there. And what values do you want to experiment it on? Let's say I want to experiment it on 2,5. Okay. Then you close the bracket. This is what you have defined as your grid. You have defined as your grid. Now, what is the next step? Once you have defined your grid, we are going to actually implement. We are going to implement grid search. How are we going to do that? We are going to use GridSearchCV, this one, and we are going to provide what? Estimator. Which model are you using? Random forest model. I'm using random forest model. Okay. And I will also provide a random state equals to any number. It can be any number. If you want to repeat the same numbers at your end, use the same random state numbers wherever, whatever I have used. If you want a different one, since there is some randomness, it will give you a slightly different number. It will not be exactly the same. Okay. And in parameters that I wanted to search, I'm passing this. I'm passing this. How many folds? We already saw an example. We are also doing 5-fold. We are also doing 5-fold. So 5 folds are going to be looked at. It's going to be looked at. Then all of this is stored in grid search. Let me call this as RF grid search. And we are going to do this. And let's also store the time. So here we are going to say start time is this. RF grid search grid RF grid time. We are going to say time dot time is equals to this, and we are going to do the predictions. We are going to do predictions, but what I need to show you guys is let's copy it. Let's copy it, and I'm going to say with grid search cross validation. Okay. And I am going to say this. Let's replace all the values or all the variables. This is going to be white rain, but here I want it to also show me best parameters. I also wanted to show me the best parameters. So we are going to say we are going to here best parameters is nothing but text underscore RF is equal to grid search best estimator, and we are going to save our best params in best params. RF. Okay. Okay. And we are going to use the best model to do our predictions. We are going to use best model to do our predictions. Which is this. Okay. Cool. Let's also replace it here. Best RF. Let's call this we'll have to check. RF tuned GS. Okay, grid search. RF tuned grid search. This also is fine. This also is fine. And everywhere else, this is the same thing. Okay. So let's also print the best parameters. Best parameters. Let's run this. Now, since grid search is running this multiple times, even the combinations and cross validation is also happening. You will notice it is taking time. Cool. So the results are out. Okay. What is happening here? In random forest grid search CV, it took how much time? 55, close to 55 seconds. Here it was taking how much? 1 second. And in decision tree, only 2 milliseconds. 2 milliseconds. Okay. And let's also see now This is your best parameters. The variant of random forest, which is giving the best performance, is having a max depth of 10 and minimum sample split of 5, and your n estimator is 300. Your n estimator is 300. Okay. Now, do you notice the gap between train and test has reduced? Train and test has reduced. Now, training earlier was how much? 98%. 98%. This was 77%. What has happened here? That from 98, it has come down to 93%. And test accuracy has gone up by 1%. Has gone up by 1%. Okay. Okay. Cool. Cool. And if you compare these metrics also you will compare, you will see that I think it is improving on your the ones which did not die, which did not survive. So this is 82, 72 precision. Here it is 83 and 68. Sorry. So on the one, it is improving. Your precision is correct there. Okay. Cool. Cool. Now let's also do the same thing. Let's also do the same thing with random forest. Oh, random search CV with random search CV. So here we are going to, like for grid search, we were using grid search CV. Here we are going to use random search CV, and then rest of the steps are exactly the same. I can, still keep using this parameters. I don't need to define it since it is already here. What I can do is I can copy all this. I can copy all this. And instead of RF grid search, we will say it is random search. And here also, this will change and it will become random search. Parameters are still the same. This will become RNDM, random time. RF, this will now become RS, random search. This is going to become, we're just replacing, we're just replacing the values here. Best params, let best params be the same. Here, let this be then or NDM. GS is not there. RS is here. Then what else? What else? This will become a random time. Best params is best params. This will become RF tuned with random search. This will become predictions. Instead of grid, it is going to be random here and here. Let's run this. Okay, where are we getting an issue? Got an unexpected param grid. Got unexpected param grid. Ah, so here it is slightly different. I think this is random forest, right? I think it is parameter distribution. Like there is a slight difference in the name of the parameter. It does the same thing. Randomized search CV. So whenever you also are stuck, do it the same way. It's not possible to remember everything. Randomized search CV. We are going to open the sklearn and we are going to find the parameter. See, parameter distributions. Param distribution. Instead of param grid, you have param distributions. Param grid is what we have defined here. Okay, let's see. Now this should run. Now, what did we study? What did we study? That random search should take less time. Random search should take less time compared to grid search. Let's see. Let's see what happens. I just want to make sure I am using random search. Yeah. See, did it take less time? Did it take less time? Yes, less than half. Less than half. What are the parameters that you're getting? It's exactly the same. I think it is exactly the same. Minimum sample split, this, and even that's why the accuracy is also same. Everything is going to be the same. Okay. Here, since the data was less, the random search is giving you the same result as grid search. If you expand your parameter grid, if you expand your parameter grid, or you also have much bigger data rather than 800 900 data rows, if you have more rows, this will definitely change slightly. Okay, but here in this case it is coming out to be same. Okay, so cool. That is your random forest and decision trees, both of them with all the combinations, with tuning, without tuning. Tuning also we looked at using grid search as well as random search. We also compared the times. And from the start, you have looked at what your decision, data cleaning, data processing, how will you handle missing value, what are the different strategies that you can take to handle missing values, what are the different strategies you can take to handle outliers. Okay, cool. All right, all right. In fact, we can do one more thing. Let's Now, since this is a classification problem, we will also plot a ROC curve. We will also plot a ROC curve. What was the ROC curve? Area under curve should be maximum. Area under curve should be maximum. So let's call this, and we are going to say for this is my TPR for random forest. This is for my random forest grid search. This is for my random forest. What do you say? Random search. Okay. Once you have created all this, what you're going to do? You are going to plot. You're going to plot decision tree, and then you're plotting all of them. You're plotting all the lines. You're plotting all the lines here. Okay. You're plotting all the lines here. This, let me, instead of random guess, this is average model, just to be super duper clear. Okay, and let's put it this legend, all that is fine. Run this. See, see, all these are plotted. All these are plotted now. Which one is giving you the maximum area under curve that you can get from area under curve? That you can get from area under curve. Okay. What we can do is calculate area under curve. Area under curve for each one of these. This, this, and this. Okay. Okay. So you're getting area under curve also here. So with this guys, we've covered Random forest for classification. I encourage you guys to, I'll be uploading this Google Drive, sorry, this collab. I'll be sharing in the comments also and on the Google Drive also. So if you guys want to, you can also practice. Okay, that's it. Thank you.